Hello, I'm Professor Stephen Abbott. Welcome to the second part of crystallization science, crystallization via clusters. In the first part, we looked at the solubility science issues. This is all contained in the new Chapter 11 on crystallization in my free ebook, Solubility Science, Principles and Practice. And the apps in the book and the ones used in this video are available on my Practical Solubility website. So here I want to find what the science of crystallization actually is, assuming we've got all the solubility aspects worked out. And there's one very sad aspect of crystallization science, and it's called crystal nucleation theory. If you go to any book or paper on crystallization, they will tend to spend a lot of time talking about crystal nucleation theory, despite the fact that it's nonsense. They will describe all sorts of equations. I have them in the app, P's and J's and B's and N stars, but it is all nonsense. So I'm not going to spend any time on this. If you want to understand what CNT is, they all call it CNT, then the app is here, but I'm not interested in it because it cannot help us as practical people who want to make real crystals understand what's going on. Instead, I want to use a crystallization map. Now, I will start this map describing CNT, classical crystal nucleation theory. You have a supersaturated solution with the solute in it. And somehow a pre-nucleus appears. Enough of these things come together one by one to create this pre-nucleus. And then one by one, the solute molecules come on and make a bigger nucleus, and once the nucleus is formed, then it just crystallizes by some form of magic. It's actually true that some solutes do crystallize like this. As far as I can understand, sodium chloride, when it crystallizes, does follow this path. It's very, very rapid. But in most cases, it simply does not explain what's going on. What I want to talk about is crystallization via clusters. So what do I mean by a cluster? I mean that the solute molecules come together as a loose cluster. Here there's a very small loose cluster. Here it's a bigger loose cluster. In fact, it's a loose nucleus. We can call it what we want. But then this loose nucleus starts to say, okay, I'll become a crystal and will crystallize. That's not very different from CNT, but it's starting to stress that clusters are the important part of the game. The existence of clusters is not controversial. If you do just about any analysis with neutron scattering or X-ray scattering, you can find clusters. And I'm not enunciating any new theory. There are plenty of people who work on these cluster ideas. My book is trying to bring them all together as a big single crystallization map. Now let's see what happens in real life. What we have in real life is heteronucleation. We have a supersaturated solution that has some junk in. And what happens is that the loose clusters like to associate with the junk. Why would they not? And you can then start getting nucleation around the junk, and then that starts to crystallize. Now, CNT is supposed to be a pure theory, and people do all sorts of experiments, but they all agree actually most of the time that you get a crystal spontaneously forming, it's heteronucleating. So most of CNT is worthless because most of what's going on is heteronucleation, and I'd rather think of it as heteronucleation via clusters rather than via CNT. But we can also get oiling out. So what's the difference between loose CNTs? Here we have a loose prenucleus, we have a loose nucleus, and then it decides to crystallize. But in the first video, I showed metastable app, and you can get oiling out. The first three panes of this are identical, I just copy-pasted, but this large cluster becomes even larger and you get liquid-liquid phase separation and it falls out. Not as pure glassy solute, but solute plus solvent, say 60 solute, 40 solvent. Very famous is the two-step nucleation theory. You have a supersaturated solution, you have a loose cluster, you get a bigger cluster, and although it was impossible for the crystals to form spontaneously out in the solution because the surface energy of these little clusters was too high when surrounded by solvent, now it's surrounded by itself as a loose cluster, so it can start to crystallize, and that then gives you your crystal. There is no doubt that two-step crystallization exists, and it's especially clear in protein crystallization. All the famous papers on two-step nucleation describe this in proteins, and there's lots of evidence for it. In an extreme, before these appear, you could get a very large loose cluster. In fact, it would be equivalent to an oiled out drop. So you haven't got a big blob come out, you've got a little drop coming out, and then that drop can start having these clusters inside. There are many variants on this. So I'm not against two-step, it absolutely exists, but it is only one of many possibilities. Now, people say, once we've got a crystal, everything's fine, it just grows. So we get a depletion zone, the solute starts coming to the crystal surface as individual molecules, they start getting incorporated into the crystal, and because they've come out of the solvent, you've got a depletion zone, you've got less around here, so there's all sorts of kinetic restrictions on how fast the crystal can grow. But that's the classic growth scenario. Many people say it's impossible and you need BCF theory and all that. I don't care. It's not how it works. Much more important is crystal growth via clusters. We have our protocrystal, and instead of just having individual molecules arriving, we have surface clusters forming. There are precedents for this. Famous scientist Botzaris has come up with nice explanations of how this might happen. But the point is, you get these clusters forming, and then it's these clusters which start to crystallize and grow. And so you get your large crystal via clusters. But there are variations. You can get crystalline clusters. So we have, via some loose clusters, formed some microcrystals sitting on the surface of the crystal. Now, what can happen? Well, some of them assemble, so we start getting stuff happening, and this one has got significantly bigger, and this one hasn't done much. And this one has actually rotated, so it's now being incorporated into the big crystal. So there are three possible outcomes when we have crystalline clusters forming on the crystal. We have crystal growth here, we have this small one going off and doing whatever it does, and here that's probably going to be a seed crystal for secondary nucleation. Here's a nice one. It's called loop macrostep purification. I don't know why it's called a loop macrostep. That's a terminology used by the professionals. We happen to have an impurity getting in the way of the crystallization. So you can't really grow over this impurity. Along comes a cluster. That's what I would call a blob, a cluster. It's called a loop macrostep. And now this impurity is actually happy to be dissolved in this material. So it gets dissolved, and as soon as it's dissolved, the real solute comes in and takes its place, and so you now start growing, and the impurity is actually swept out. And there's lovely evidence for this. So that's the loop macrostep purification. If you try to crystallize too fast, you get surface clusters forming, as we've seen before. Then we start getting dendrite growth. We have so many clusters, they're so big, they're so compact, you get these very dendritic crystals with bits sticking out all over the place. They're not the sort of things you want. They can easily bring in impurities, they don't handle very well. So that's when you've gone over the metastable zone width and are crystallizing too fast. I mentioned secondary nucleation. There's lots of confusion about how this works. Here's my take on it, again based on clusters. We get surface clusters forming. We now get some large clusters on the crystal. Now they might choose to grow just to make a big crystal. But if there's some sort of flow, if you're stirring it, if you tap it, if you slide it along the bottom, then there are multiple experimental ways to do this. You sweep off this loose cluster, and that is large enough to produce a significant seed, which then grows as its own crystal. And there's one variation, and it takes us back to the opening picture, which was of those big calcium sulfate crystals. If you look at them very closely, they aren't actually very perfect crystals. What happens is that you get mesocrystals growing in a loose cluster, and then you get more mesocrystals growing, and then these mesocrystals come together to form a final crystal. If you do an X-ray of the crystal, it looks like a uniform crystal, but if you look very closely, you find that there are little nanoclusters coming together to make this mesocrystal form. Sometimes they're so perfect that it's really just one crystal, sometimes they're slightly imperfect, and sometimes they actually have stuff around, and that's when you're into biomineralization, where you have all sorts of other effects. So this one set of descriptions, the crystallization map, allows us to see all the variations of crystallization that I've heard of, all described rather simply via clusters doing one thing or another. If this cluster-based approach is correct, then what do we need? We need to be able to generate lots of clusters and examine them. We need a cluster factory. And I and others are working on the possibility of routinely looking at clusters in a scientific way and seeing how they interact with crystals, with junk that you put in which does heteronucleation, whether they grow spontaneously, whether they are actually semi-solid, or whether they're fully liquid. So can you filter them or not? These are all questions which will help us crystallize much more intelligently in the future. Goodbye.